Excellent.
Yes,
I guess you don't want me to sit in front of the camera?
yeah, that would be best not.
Handshake.
Well, where's best for me to sit, do you think?
It doesn't matter if you sit in front of the camera, actually.
Well, considering it's Joe, I'd put Joe in charge to make sure the camera's doing the job, wouldn't you?
Yeah, I might sit here and make sure it doesn't switch itself off.
Should have. Hi.
You might get more.
Is this going to be filming? Do we need to be out of the way of it?
You can sit here, it's fine. As long as I
the
know
board.
how I'm talking. It's just
Okay.
so that I can improve on how I talk. You can sit here.
Are we allowed to eat, sir, or not?
I don't mind. Don't spill anything. Michael likes to smell fish and chips.
How many are you expecting, Michael?
Max 5.
Right, I reckon you're getting more than 5, mate.
So it's an intimate.
I wonder whether I can find.
Do you want blinds up or blinds down, Michael?
I honestly don't mind. I think it's good to have some light. But
Yeah.
Maybe close the see-through ones.
You
there
could
might be
probably
a
get,
bit
if you're using the
distracting.
visualiser, it might be an idea to shut that light. I always do, because you can't visualise, you want to
Hey,
control
Matt.
I don't think I am
I thought it
going
was
to
going to be Michael giving a talk.
Okay.
You didn't know?
No, I didn't know.
just in case of glare.
I am taking notes, yeah.
Email it to me.
Yeah, sure. I'm recording the classes. Are you recording, Michael? Yeah, you are recording, right.
My witty batteries.
Oh, we've got non-year 12s.
Around here. Probably smarter than us.
I know. I wasn't expecting non-year 12s.
Yeah, we've got 10s, 9s as well. Going up, stay on.
Yeah, hello.
Okay.
Oh yes, everyone should have a handout. I wasn't expecting
Well,
this anything from
you've already
someone.
got more than you're expecting, mate.
Okay, yeah, I honestly wasn't expecting
Nice.
so.
I told you were going to get about 20, mate.
I've got 19 just.
You've got 19. Well, it looks like you're going to get more than 5 teachers.
Oh dear, I did not realise.
Thank you.
We can share.
I can't see which ones are blues and which ones are blacks.
Yeah.
Yeah,
I think top ones are blue and top ones
I don't know. I'm going to have a look. Can't actually see.
Is it just the top
These
three?
two are black. These three are black.
These two are
Those
black.
blue. Yeah, top of blue.
Yeah, I need to
Top
draw.
of blue, bottom of black.
All blues.
Not to have a naughty crossing.
Yeah.
Yes.
Oh wow, okay. More people. I won't give you that handout.
Looks like all the notes have been taken already for me.
Thank you.
Michael is right now.
Oh dear.
Hey, Jack. Jack.
I have a few more, but that should last for
It's
now.
not doubling up. I'll double up.
It's okay, I have fine.
Are you sure?
Ideally, it'd be nice if people can take these away as well.
That's great.
And basically,
We understand the question.
The top line dot, can you join each top line to each bottom line?
Oh, no.
You can't.
No, I've seen this before.
Unless you go around the wall.
Okay.
Yeah, you
Why?
can. Close. I've seen it, yeah, I've seen it before. It can't be done in a plane or a sphere.
You can be down on a sphere.
I think you're on a torus.
You can be down on a sphere.
How?
You can be down on the globe. You have to take one round the whole sphere.
No, I thought you needed to take 2 round, one round one axis and one round the other. That's what happened on torus. Show me then. Show me. You've got a pen, you've got paper.
I don't know how to do it exactly, but I know you can.
It's the 330s, isn't it?
Yeah.
So basically,
No, except for one sphere.
well, I mean, if we were in 3 dimensions, yes.
Yeah.
So,
I did not realise that this way.
Yeah, I'm moving.
Okay, I was expecting
We'll put the chairs back.
I only anticipate maybe 5 more. Thank you very much.
Yeah, you got a lot more than you expected, mate.
Yeah, just to start, I thought I was expecting about 5 people. So this is a bit more people than I expected. Yes. Yeah, you can have a go at that whilst we just. Okay. Okay, so now I'll start. So, yes, this is a talk about graph theory. Okay, so this is a talk about graph theory. But in year 7 and 8, you might be taught that a graph looks like this. And you're right, that is a graph. But just as orange in English has 2 meanings, graph also has 2 meanings. And in graph theory, what we want is this sort of thing. So I'll make dots big. And also, if you have any questions, feel free to ask as we go, because I really want everybody to understand. So what we mean by a graph in graph theory is not this type of graph. We mean many vertices, so each of these are vertices connected by things called edges. Okay, and I put that on the sheet. So a graph is a set of vertices connected by edges. Nice and simple. Okay, now let's introduce another terminology. So let's make this slightly more interesting. We're going to define a function called the degree of a vertex. Degree of a vertex. The degree of a vertex is defined as the number of edges coming out of the vertex. Okay, and just to test that everyone has got that idea, let's go around this graph saying what each of the degrees of the vertices is. So, change color. What's the degree of this vertex? 2, yes. And this one? 2. And this one? 4. This one? 2. This one? 2. Oh, look at that, they're all even. But that's not always the case. But okay, so this talk is basically going to go through a really useful theorem at the start, and then we're going to go through 7 problems, the last of which is my favorite. So first of all, let's prove this theorem. So our first theorem. And this is very useful, as we will see in the problems that are coming up. We want to show that the sum, can you see it there? The sum of the degrees of all of the vertices in a graph is precisely equal to 2 times the number of edges. And we're going to use capital E as the number of edges from now on. We're also going to use capital V for the number of vertices, and F for something else that we'll find out later. So does anybody know why that's true? Okay, so we're going to prove it using quite a nice proof. To start off with your graph having no edges. Okay? Let's make a table. Number of edges, sum of degrees. When you have 0 edges, what's the sum of the degrees? 0, nice and simple. Okay, let's add 1 edge, this edge. What happened to the degree of this vertex? It increased by 1. And this one? So what has happened to the sum of the degrees? Increased by 2, exactly. 1 edge, the sum is 2. Let's add another edge. What's the sum of the degrees now? Well, this one has increased by 1, increased by 1, entirety has increased by 2, 4, 3, 6, 4. And then you get the idea, and that's our proof. Right? So why is this theorem useful? Well, let's apply it to the first problem. Okay. Now, if there weren't so many tables in here, I would ask people to get up and start handshaking with everyone else. But seeing as that's not possible, let's just go straight on to the problem. Problem 1, the handshaking number. Okay. Well, we might as well try this. So everybody, you can start handshaking with some other people, and you have to count the number of times you've handshaken. Okay? And whilst you're doing that, I close it. Make sure you count correctly. Don't count incorrectly.
How do you do?
Everybody in the room.
Handshake at the end.
I'm a counter. I'm a counter.
Okay, good. I really hope everyone's got this right.
Can't remember.
Okay, I really hope everyone has counted correctly. I really hope everyone's counted correctly. I realise this will all work. Thank you. Okay, I'll start off by saying that I shook hands 4 times. Yeah, I wasn't expecting this many people, as I said. So now we need to go around and everyone will say how many times they shook hands. Alright, good now. We have a handout. Yes, we just went shaking hands, but you've shaken hands with 0 people. Okay, so now let's go around and everyone will say the number of times that they shook hands. So 4, no, if you just keep going.
6, 7.
Oh, actually, let's do it quickly. Yeah.
2,
2.
10,
Do you show it?
8,
8.
12.
9,
Yeah. Oh, no.
8,
8.
15,
15. 9.
8,
8.
6,
6.
10,
Okay, 8, 10. 8. 9.
12.
12. Oh, there's another 9 just there.
Yeah.
Yeah.
6.
6. Okay.
I've got lots of friends. 21.
No, is that everyone?
7.
Yes! that's good. That's good. Okay. How many odd numbers are there? 8. And in fact, no matter how we shake hands, this number of odd numbers will always be even. And that's something that you encounter in D1, but there's actually much more to graph theory than there is in D1. Let's actually prove this. So, having people shake hands is quite contrived, so let's put it into graph theory and make it a lot clearer. Let's use a graph. We're going to denote the people as vertices, and we're going to denote the handshakes by an edge. Did anyone shake hand multiple times with the same person? No? That's good. That makes it easier. So let's have a look at this. So this is where we start using our theorem. So the sum of the degrees is equal to 2e. Now let's split this sum of the degrees into all of the possible degrees that we went over. The sum of the degrees is equal to lots of even numbers, plus lots of odd numbers. And we're just denote them like this. Does everybody agree with that? Yeah? What's the sum of the degrees? Is it even or odd? Why is it even? Yeah, it's 2 times the number of edges, which is an inch. So this is even. Okay. Now what's the sum of even numbers? Even or odd? It must be even. So what's the sum of odd numbers going to be? It has to be even as well. But if you add together an odd number of odd numbers, then what do you get? You get an odd number. So So that means there must be an even number of odd vertices. Right? Does everybody get that? Just one more time, just for the people who didn't get it. So the sum of the degrees is even from this theorem. Now, if we split the degrees into lots of evens and odd numbers, then the number of odd numbers must be even, otherwise this would be odd. And that's quite true. Okay? And that's quite powerful. So let's move on to problem 2. And this is where I want everybody to get a piece of paper and a pencil. If anybody has no paper, then unfortunately I have no paper.
I've got two. But I don't include it.
Everybody wants one? One more small one?
I don't need paper, it's just that.
How are you? You look at cello.
Okay, so here's your challenge. Okay, here's your challenge. You have 6 vertices, and all you have to do is connect every single pair of vertices by a single edge. Nice and simple. However, each of these edges must be blue or red, but if you don't have blue or red, just do dotted with that, or dotted or solid lines. And your challenge is to have no triangle of just blue or just red. So you're not allowed to have something that looks like this, or that looks like this. Okay, so if you just try that for a bit, then we'll go on. So remember, you have to connect every single pair. If anybody does it, please tell me.
Yeah, I've already found it impossible.
Oh no, you have to connect every single pair. So
Oh, so that's right. Everyone should have to do it. Can't do that.
You can have 2 edges.
I can see what's glaring out.
As in, what happens is when you have 2 solids.
So I started simple, I started this one.
You have
Straight.
It's all great.
apart from this line. But there's also this one. And like, if you just keep, yeah. At this moment, I might mathematics.
Yes, please do.
Okay, so let's reveal something, but to keep up the suspense, I'm going to tell you one piece of terminology. This sort of graph is known as a complete graph. And although it's not essential that you know this, it might be just good to know about it anyway, as if you're talking about graph. So the complete graph on n vertices, is basically what it says on the tin. Say you have 4 vertices, then you connect every single one like that, and that's the complete graph of n vertices. That's quite a long name, so we also call it Kn. Okay? So can anybody tell me the name for this one? K6, exactly. But anyway, back to the problem. It turns out that, unfortunately, I told you to do an impossible thing. It is actually impossible, but why? Does anybody have a proof? Otherwise, I'll go straight. So, the key idea is to consider one vertex. Let's consider this vertex. It doesn't matter which one we consider because it works symmetrically all the way around. Now, from this vertex, we know that there are going to be 5 edges connecting it to its neighbors. Yeah. Now the the crux of the proof comes. There will always be 3 blue lines or 3 red lines. Right? Because if there wasn't, there could be at most 2 blue lines and 2 red lines. But we have 5 lines. So no matter how we do it, we will always find 3 blue lines or 3 red lines. If we had 4 blue lines, then we could find 3 out of the 4. Right? Okay, and that's exactly it. We're almost done. Now consider your 3 edges of the same color. And look at these edges. Can this edge be blue? No, so it must be red. Can this edge be blue? No, so it must be red. But can this edge be blue? No, so it must be red. But look, we just found a red triangle. So that means it's impossible. Okay? Okay, so that was quite fun. Let's move on to some more special graphs. So we're going to move on to problem 2, problem 3, sorry. And I'm just going to move this. Does anyone have any questions at the moment? No? Okay. If everyone just digests that in result first. Right, okay, so let's move on to a special type of graph called a planar graph. Now this is something that you're definitely not doing. So a planar graph is basically one that you can draw without the edges crossing. So I'm sorry for asking you a trick question, but is this graph planar? K4, is K4 planar? Well, yeah, it actually is, because the definition, why? Exactly. So, as Jack correctly said, you can do that, and now there are no edges crossing, so you're okay. So just to really, really emphasize what I mean by a planar graph, it's one that can be drawn with no edges crossing. Okay. So we're now going to prove something that seems quite dull, but it actually is very useful in something that's coming up. We're first going to show that, so let's look through it. We're going to show that for any simple planar graph, a simple graph is one with no loops or multiple edges. So every pair of vertices can only have 1 edge or 0 edges, no loops. So this would make it non-simple. So for any simple planar graph, the number of edges is less than or equal to 3 B1 sets. Okay, and this calls for another puzzle that you can try. If you have 6 vertices, can you draw 12 edges connecting them so that they don't cross? And remember, you're not allowed to have multi-edges because the graph is simple. So doing this is cheating. Okay, so I'll just say that again. 6 points can you draw 12 edges such that no edges cross? Okay. Yeah, what's up? That's a multi-edge, and that will make the graph multi.
Is that cheating?
No, it's fine. It's okay. It's fine.
So I did the 8
Yes, some people have got it quite quickly.
I stepped over 2, so it wasn't close.
If you want some extra problems to do, you can dip it over, and there are some further problems there. But we'll be going back to the main stream. If you've done it with 12 edges, can you do it with 13 edges as well?
Is that what you like to do that?
Yes. So now can you do it with 13 edges? So you've done it with 12.
That's 13.
So I'll show you the one for 12. So you just... There you go, that's for 12. Can you do it for 13? Can anyone tell me why? It's right there on the board. Yeah, so if we work out the right-hand side, 3 times the number of vertices, 18 minus 6 is 12. The number of edges in a planar graph with 6 vertices is at most 12. That tells you that for any such graph with 13 edges, you cannot draw it without edges crossing. Okay. But we're actually going to prove this now. Okay, and to do that we need some machinery. We need Euler's formula. And Euler's formula is not too difficult to prove, but I'm not going to prove it here just for the sake of time. If we define a face as something bounded by edges, and we also count the outside face, can anyone tell me how many faces there are in this diagram? 8 is absolutely correct. Not 7, because we also count the outside faces. It's like splitting the plane into regions, okay? Euler's formula tells you that the number of vertices minus the number of edges plus the number of faces is always 2, no matter what you do. And let's actually do it for this graph to show that I'm not assuming anything incorrect. So what's the number of vertices?
6.
Yep. Number of edges? Number of faces? Great. And if you, whatever you do, if you have a simple planar graph, this will be true. Okay. And now comes the crux of the proof. We're going to count the number of face boundaries of each face. By face boundary, all I mean is something that encloses a face, something that encloses a face. So this is an edge boundary, this is a face boundary, face boundary, face boundary. Okay? And I claim that the sum of all the face boundaries, yes, do say if you don't understand, because I might not be explaining this to you. The sum of all the face boundaries is greater than or equal to 3. But why? Well, each face must have at least 3 edges. Or face boundaries. So each face must have at least 3 face boundaries. Is that true?
Yes.
Yes. Because we omitted loops, which would be 1, and we omitted multi-edges. So every face must have at least 3 face boundaries. It must be at least a triangle. Yeah? So that's true. But what has the sum of the face boundaries got to do with the number of edges? It's twice the number of edges, because every edge is counted twice by each face. Right? Okay, that's a quite difficult statement to digest. So if we count this face, and we count the number of face boundaries, then we're counting this edge twice when we do it for this one as well. Yeah? And when we go across all of the faces, we will be counting every edge twice, because every edge is part of only 2 faces. Yeah? Okay. Hopefully you've got that, because now we're going to do something else. 2e is greater than or equal to 3f. But what does that mean about f? F must be less than or equal to what? 230. Okay? Now let's substitute this into here. First rearrange this in terms of f. So it's equal to 2 plus e minus b. Yeah? Okay? But this is less than or equal to 230. Okay? Let's move 230 over to this side. Sorry, is it too late? I'll write it over here. So if you can't see that, I'll just write it out again. So explaining it once again, from what we just did, we derived this. Is that true? Yeah, is that clear? Yeah. But we also know about Euler's criteria, Euler's formulas. Yeah. All we're going to do now is combine the 2 equations. If we rearrange it, it'll make it easy. So let's rearrange it for f. If someone rearranges this for me, 2 plus e over minus b. Yep. Now let's substitute this in. Substitute. Oh, sorry, I put this the wrong way around. Yeah. So this is going to be less than or equal to 230. Okay? Now let's rearrange this, and we get 0 is less than or equal to 2 plus e over 3 minus b. Moving the other side, moving that to this side. Get that. Multiplying by 3. And we're done. Okay? Okay, that's quite difficult. If anyone wants further clarification, please say that, really. Does anyone want further clarification? Okay. Would it be okay if I go through this one more time? Okay, so let's do this one more time. So we're saying that for any simple planar graph, I should probably write this down. Yeah, for any simple planar graph, the number of edges is less than or equal to 3b minus 6. Yeah? And the way we go about doing this is by considering each face. Each face must have at least 3 face boundaries, because there must be a triangle or a polygon with at least 3 sides. But when we sum across every single face, that must be greater than 3 times the number of faces by what we just said. But the sum of face boundaries is also equal to 2 times the number of edges.